Good morning, everyone. Something that got missed out in my introduction, but is very clear, as I'm one of the very few people without a suit in the room. So I'm a civil engineer with my sleeves rolled up, works on the site, and we will talk about the practical aspects. Like you introduced, I'm from the Indian Institute of Technology, Delhi. It is located in Delhi in India, but we have a small campus in Abu Dhabi, which is where I'm based now for the last several months. Today, I'm going to talk to you about the next part. Professor Scrivener talked about the hydration. Professor Martirena talked about the cement production. What about the concrete? Whenever there's a new product, we're worried about the properties of the concrete. How will the market react? And I'm going to talk to you about what kind of concrete you can produce. We've been working on LC3 in India for 13 years now, and we have some experience that we would like to share. You all know what LC3 is. The thing that I would like to say from this slide is that we don't compare LC3 just against ordinary Portland cement, but also against fly ash-based cement in India, because this is the most common cement available in India. And that's not just in terms of performance, it's also in terms of the cost. So there was a question on cost. We have to compete against fly ash-based cement as well, which is way cheaper to produce than ordinary Portland cement. We already know the advantages. I'm not going to talk about a lot of these things, but I am going to explain to you how we are able to reach these conclusions at the bottom about the performance of the concrete. I'll give you a bit of the background. In India, LC3 is a cement that is allowed to be produced by the standards IS 18189. It's called the Portland calcined clay limestone cement. It's also allowed to be used in reinforced concrete. Based on the research that I'm going to show you, we are allowed to use Portland calcined clay limestone cement, that's LC3, in reinforced concrete in India in almost all types of applications. And of course, there are other standards as well. But what did it take us to reach there? What have we been doing for the last 13 years is what I want to explain to you. We did a lot of work in the lab, everything from hydration to microstructure development, a lot of things that Professor Fernando Martirena was talking about, what Professor Scrivener was talking about. We've also been doing a lot of that work in India. But the important part is that we have been working a lot in the field as well. From going to the mines, to finding the clay, testing the clay, calcining the clay in real cement plants. There are many cement plants in India where we have already converted the kiln where you would be able to calcine the clay in a normal kiln. But they have started to produce only recently because the standard came out only 2 years ago. We have worked a lot on grinding on different types of plants. The actual production of the concrete, construction, normal concrete, even more advanced production of materials like autoclave aerated concrete blocks, made buildings, roads, and so on. We've also worked in the lab on the structural performance. There was a question about the structural performance of the concrete. Right now, we are making this building, which is going to be in Delhi. This is a real-scale structural engineering laboratory, where the building will also be a sample that we will be testing over the next few years. We are working on all of these things. We also work with cement companies around the world to help them not just produce LC3, but also to use LC3 in the market. So it's about going there to the field, collecting samples, working with them to produce cement. And if you invite me to your office, please make sure you have no glass doors, because I have a bad habit of starting to write on them and give lectures. Professors are kind of like that. So be careful, don't invite me to your office. We have a large team. We do dissemination events, training courses. If you cannot attend our courses, I can bore you online as well. You can find this channel online. I will find you and bore you whichever way you want. It was so good to see Professor Scrivener over here. Now we can have those boxes in every city in the world, and Professor Scrivener can give a lecture. So maybe if you are not able to see that box yet, you can go to a YouTube channel to see me instead. And like Professor Martirena presented, we also have a TRC in Africa because we realized we could not travel to Africa all the time. There's a lot of work to be done over there. We have a technology resource center, a full-scale laboratory that can do all the things that we can do in India, in Africa as well. This was set up by funding we received from a donor in India. This is a family of the largest chemical producer in India who wanted to support LC3. We helped them in different ways, but that's about what we've been doing in the background. But let me tell you what kind of performance we've been talking about. There was a question on workability. I would like to explain to you why today we are so confident about using LC3 in the field that we have been able to put it in our concrete standards. I start with workability. Everybody asks about workability and the higher water demand. There was also a question over here, and it's clear. As you go to lower water binder ratios, the water demand, the admixture dosage required increases because clay has a high specific surface area. It has those fine particles that will increase the water demand. How do you counteract is the question. How do you live with it is the question. But even before we started to answer that question, we asked another question. There's a lot of construction in India that happens without any technology. People buy bags of cement and start producing concrete with their hands, with shovels, which happens in so many countries around the world, especially in Africa, India, developing world, that happens a lot. The first question we had was, will these people, these very highly trained engineers that you see in that picture over there, will these people be able to use LC3 or not? So we did not tell them anything. We gave them a bag of normal cement, asked them to make some concrete, then we gave them a bag of LC3, asked them to make some normal concrete. They were very amused to see us make cubes and do slump tests on the concrete they were making. They were not used to seeing those tests. But the good thing was, when we did the measurements, the performance that we got with the concrete that was produced in this way was basically the same as the performance we had with any other cement. We were less worried that if the concrete was used without any technology, you would be able to produce that concrete. We said, we wanted to see if you give these very highly trained engineers, once again, some more technology, and you see the very high-tech concrete mixer over there. We gave them some technology, and we said, can you make some concrete out of it? You know, the only quality control that we did in this case was we had a bucket of water in which we put a hole on the side. You cannot put more water than that in the concrete. You control the water to cement ratio. Just by controlling that, we made this pavement 40 batches of concrete using this mixer. The average strength of the concrete was 53 megapascals. Just made this way, volume batching. This was in 2017, and you can see the beautiful concrete that was prepared. Yes, clay has a higher water demand, but even without a lot of technology, you can make beautiful concrete, high-strength concrete. This, by the way, is the exit gate of a cement plant in India. We had just finished producing LC3 in that plant in the end of 2016. In 2017, January, we decided to make this road. 5 years later, I went back. You see the truck still going over that. That road is doing perfectly fine. In fact, you see the part that was not made with LC3 has some abrasion. This part, 5 years later, still doing fine. This picture is from 2013. Even now, things are fine. The other thing that we also talk about is the loss of workability with time, the slump retention. Yes, workability can be lost very quickly in the case of calcined clay. You have to rely on chemicals. That's the important thing. If you use the right chemicals, various additives, these are simple additives. This is nothing very expensive. One of the companies said, you're going to do something very expensive to the concrete. So I said, let's try this. Let's squeeze a lemon. Let me tell you this. If you squeeze a lemon and put 0.05% of lemon juice per kilo as a weight of cement, 0.05%, you will reduce your admixture dosage by half, and you will get 2 extra hours of workability. Lemon juice. Just squeeze a lemon in that. This is not going to be expensive. Of course, lemon is not the best admixture in that case. There are other chemicals that are better, but just to give you an idea that you do not need something expensive, you can increase the setting time, you can get good workability. You see on the right side over there, a picture of a self-compacting concrete 2 hours after it was prepared. This is using LC3. If you're asking me why it does not look red, because by the time you make the concrete, the red color is diluted because of the gray color of the sand. And by the way, this clay was also a higher grade clay, so the workability loss was worse, but the iron was less in this particular case. So that's about the workability. We can handle it. I promise you we can handle it. And if you're having issues, talk to us. We will help you handle those issues. Mechanical properties, this was not something we were worried about from the start. The strength that we get in the concrete at 28 days is essentially what we expect with the kind of aggregates that we have in Delhi at the specific water binder ratio. The strengths that we are getting, compressive strengths, are pretty much similar, but compressive strength is not where the world stops. For structural design, you need a lot of other things. You need the flexural strength. Once you have achieved the compressive strength that you want in your concrete, you will get pretty much the same flexural strength as any other cement. Once you have achieved the compressive strength, you will achieve pretty much the same tensile strength in the concrete, pretty much the same elastic modulus of the concrete, pretty much the same bond with the reinforcement. So I'm also a structural engineer. As a structural engineer, I'm not worried about the mechanical performance of the concrete, but I still have to demonstrate that it works. So we made reinforced concrete beams, slabs. We also made pre-stressed concrete beams, very long pre-stressed concrete beams. For the last 2 years, we have been monitoring the loss of pre-stress in the pre-stressed concrete. It's no different from the ordinary Portland cement. We are essentially having the same loss of pre-stress because we realize it depends more on temperature than the cement type. But just to show you the results, we've been working on concretes even with 0.3 clinker content, and you can see even with 30% clinker content, you can design concretes to have a similar strength as 50% clinker and even as OPC. So with 30% clinker, you can still go to the similar kind of strength in the concrete. A lot of structural tests in the lab, beams broken. I'm a civil engineer, like I said, I like to break things all the time. And we broke all those things, we did some measurements. LC3 30, LC3 50 performs very similar to OPC. Be it the flexural load that is being measured, be it the shear capacity that you're measuring in LC3 30, LC3 50, OPC, be it the deflection that you're measuring, be whether you measure it in the case of slabs, in the case of beams, you essentially get results which are very similar. Creep seems to be lower from the literature, shrinkage seems to be similar. Creep is a question that we have to answer because there's a lot of, you require a lot of facilities to be able to measure creep. But then, like I said, the most important application for creep is pre-stressed concrete. From the measurements that we are doing on the pre-stressed concrete, we do not see much of a difference from OPC and LC3. So we are very confident about those things. And the reason we wanted to understand why, you've taken cement. You know, as people working on cement, we love clinker because clinker is the most reactive part of cement. We are able to remove that clinker, we are able to replace it with less reactive materials and still achieve good strength. We wanted to understand why. So one of my students who later went on to work in Leeds, while working over there, realized that the interfacial transition zone holds the key. The interfacial transition zone produced using OPC looks like this, produced using LC3 looks like this. Don't go by the cracks. These cracks are because of sample preparation. You get a denser interfacial transition zone that gives you a better strength of the concrete. You have a more efficient microstructure. You don't have those weak zones, which is why LC3 performs better. And because you don't have those weak zones, the pore properties also increase. The pores are finer, they're less connected, and the concrete has a lower permeability, lower chloride ingress, and so on. What this means is that the pores are finer. If you look at the mercury intrusion porosimetry graph, the breakthrough diameter of the pores is lower in the case of LC3. We've been seeing those results for a long time. What this also means is that the resistivity of the concrete is way higher. So you can see here that an OPC concrete made with 0.4 water to binder ratio has a lower resistivity than an LC3 with 0.6 water binder ratio. So for applications where durability was your concern, for example, chloride ingress was your concern, and that was the only reason you were going with a low water binder ratio, you can now live with a higher water binder ratio because the chloride ingress is much slower in these cases. And you see those chloride ingress values over there. You see over here the chloride ingress value in the case of OPC, in the case of LC3. You see the chloride ingress in the case of OPC at 0.4 water binder ratio versus the chloride ingress in LC3 at 0.6 water binder ratio. So durability-wise, this is way better. Chlorides, one, because of the finer pore structure, second, because of the more efficient chloride binding that you get in the case of LC3, are not able to penetrate beyond the first few millimeters into the concrete. They're just not able to go in. And because they're not able to go in, your steel is better protected. We now have results on corrosion, of reinforcement, and of course, you don't see any corrosion because the chlorides are not there. So applications where chlorides are an issue, you just don't need to worry about it. Where do you need to take special care? It's carbonation. I'm not saying you should be worried about it or you should stop using LC3 or any low clinker cement. The thing is, whenever you move from a higher clinker content towards a lower clinker content, like you are in this scale over there, you will notice whether you're using fly ash-based cement or slag-based cement or a composite cement or LC3, whatever, the moment you reduce the clinker content, carbonation depth in your concrete is going to increase. How do you take care of that? There are two important things to take care of that. One is, you make sure you have the right water to binder ratio. Second, you provide the right clear cover. The standards have it right. In fact, after doing all the tests that we've done on LC3 concretes in the lab and looking at the results from the field, so we have had reinforced concrete specimens sitting out in the field for 11 years now, and in 11 different climatic conditions. And we have been monitoring those reinforced concrete elements. And what we notice is the results, the recommendations, that are given in the standards are sufficient. Whether you look at the European standards or the Indian standards or the American standards, the recommended values of clear cover and water to binder ratio are sufficient to take care of the design life they're usually expecting. Just to be safe, you just make sure that quality control is good on the site. You cannot compromise on clear cover. You cannot compromise on the water to binder ratio when you go down to low clinker cements. And that's essentially all that you have to do. Follow the standard requirements and you're safe. That's what we're trying to tell you over there. And well, if you want to be extra safe, we've got some more solutions for you. For example, this is a case of carbonation depth, and that is how much of transport happens in concrete, measured using different tests. To be very simple, this is an LC3. This one over here, is an LC3 with a certain chemical simply painted onto the concrete. This is a silane that has been impregnated from the surface of the concrete. Not only does the carbonation depth in the concrete reduce if you're painting this on the surface, it's also the transport properties of the concrete that become that reduce. That means the risk of corrosion reduces significantly. So anything that's below 1 means the performance is better than OPC. We have over 100 years of experience with reinforced concrete, made using ordinary Portland cement. If you just use these paints, the performance of low clinker cements becomes even better than ordinary Portland cement. So the experience that you have this far is sufficient. That's why the standards are also working, by the way. So one of the things that you realize that the most common excuse that we have for not going to lower clinker cements is carbonation. We know already the lower is the clinker content, the lower will be the CO2 emissions. If you go from a cement that has 90% clinker to a cement that has 30% clinker, the CO2 emissions per ton of the cement will reduce significantly. These numbers are for India, would be different for other countries. This also means lower costs. We know that. And this is good news for development. We know that. But the excuse that we have is lower clinker means higher carbonation, means worse performance. So, something that we have to, I'll skip a few slides, sorry. Oops, something wrong with the slides. So something that you realize is that, one, not all concrete is going to be reinforced concrete. And then secondly, if you're able to take care of the risk of corrosion due to carbonation, either by using these chemicals that you can apply on the surface, or just by having the right water binder ratio and the right clear cover, you would be able to reduce your clinker content in the concrete without a risk. So there are also other things that we are working towards. There's a RILEM committee right now, which is working on performance-based standards. Here is an example. In countries like India, we have fly ash still available. Well, fortunately or unfortunately. Unfortunately for the environment, fortunately for the cement industry, because it's available at a very low cost. Now, things that we've been developing are, if you can have a part of calcine clay and a part of fly ash along with the limestone, you can reduce the problems that you have in the case of fly ash cement. Like the lower early strength can be increased. The setting time can be improved in the case of fly ash-based cement. So in the end, I feel we have to move towards performance-based standards.
you have to use whatever material is available locally. The standards cannot prescribe anymore saying that you have to put X amount of this and Y amount of that. You have to eventually move towards whatever is available locally, and for that, these performance-based standards have to be developed. And we've been working on fly ash, slag, biomass ash, lots of materials, and we see that there are some basic tests that you can do in the lab. Of course, it mixed along with calcined clay. There are basic tests that you can do in the lab that can help you design a cement that works for your market. So there's a lot of work that still needs to be done for LC3. A lot of it is on the market side. What I feel is that this is a new cement, relatively new cement in the history of cement, and that's why a lot of people are worried about it. That's why all of us in the LC3 team, be it Professor Scrivener, Professor Martirena, or I, we have been working with the industry trying to convince them, to demonstrate to them that the performance of the concrete is not worse than the concrete they have been already making. It can actually be better, even though you have such a low clinker content. We have to support that, and I see Turkey as a very good example because, as Professor Martirena said, Simpor was the first company to start producing LC3 commercially, and so this is the place to start doing those innovations. And LC3 is not a dream we have for the future anymore. We never realized this 13 years ago that it would move this fast, but these are the countries, Professor Martirena also showed, where some kind of activity related to LC3 is already happening. A lot of activities happening over there. Just to also add to what I have been saying, these are pictures from Colombia, and you see big structures that have been built using LC3 in Colombia and Latin America. There are other buildings as well, other structures as well in Europe, for example, in Switzerland, in Denmark, as examples that you can see. There's a lot of work that has gone into this, but in the end, what we see is you can get the same performance in the concrete that you expect, and that is the key. A lot of people have worked behind this. This is my current team based in Delhi. Thank you so much.